On our way to linking Newton's second law of motion with the ideal gas law, I need to spend a bit of time on a few small topics. The first of these is mean free path. Since the ideal gas law is built around an ideal gas, real world gases aren't ideal. For an ideal gas, remember, we say that the gas molecules only interact with the vessels of the container, which means that they never collide with each other. Now, this isn't going to happen in reality. In reality, the molecules have some size, and because they have some size, they will travel and occasionally hit another molecule. So here we'll bounce off somewhere else, then we'll bounce off somewhere else again, and so forth. And so you'll have some sort of a random path that you take. But you want this path to be long compared to the dimensions of the molecule and compared to the average spacing of the molecule. Then what they'll mean is that there's only a handful of collisions before you hit the walls of the container, at least comparatively speaking. So to characterize how ideal your ideal gas is, your not so ideal gas is, we characterize the average distance that you have between collisions. We call that the mean free path. And we use the symbol lambda for that. And just a quick reminder of how to draw a Greek lambda if we use our special paper that we used in second grade. A lambda looks something like that. All right. So this is going to be the typical distance between collisions. And so what we'll do here is model our atoms as hard spheres. And I'm not going to spend forever deriving this, but the basic idea is you think that as our hard sphere is traveling through here, it'll have a collision if some other molecule, which we're also characterizing as a hard sphere, butts into the cylinder being swept out by the molecule we're thinking about. And so we'll say that this, when we get to this point here, is when we'll have our collision. And so we'll say that this is our typical, that if this is a typical distance here, this would be our mean free path. The derivation is a bit tedious, but it comes from just thinking about how often you'll have a molecule sitting in the cylinder, having a bit of a piece of it sitting in the cylinder. I'll just go ahead and quote the result. The mean free path turns out to be 1 over 4 square root of 2 pi times the number density. So this is the number of molecules per volume times the radius of the molecule squared. So again, remember, we're modeling this as a hard sphere. There is a way to extend to make this work for more real-world quantum mechanical atoms and molecules, and you get basically the same result. But now let's just go and think about, say, a hydrogen atom. A good number to use for its diameter is 1/10 of a nanometer. So that will be a nanometer's 10 to the negative 9 meters. So this is 1 times 10 to the negative 10 meters. That's a good number for that. So let's think about what the mean free path of hydrogen, of an atom in a gas of hydrogen would be at STP, standard temperature and pressure. So that's 1 atmosphere of pressure, 0 degrees temperature Celsius. So we can use a result from chemistry that at STP we have 1 mole of any ideal gas occupies 22.4 liters at STP. And then we can use that to go ahead and calculate our mean free path. So here this would be 1 over 4 times the square root of 2 pi. And then remember, we've got our number density coming in here. So if 1 mole occupies 22.4 liters, we can just put in Avogadro's number up in the numerator, 6.022 times 10 to the 23rd. And we'll say 22.4 liters. Now, ultimately, we want to get this all into meters, so we can remember that 1 liter is a thousandth of a cubic meter. And then for the radius, well, we had that the diameter was 10 to the negative 10 meters. The radius would be half that. Square that. And if you punch that all through your calculator, you will get 8.37 times 10 to the negative 7 meters, which doesn't seem like a very long distance. But let's think about this for a moment. That's 837 nanometers. Now, we can compare this against the diameter of our hydrogen atom, which was 0.1 nanometers. So we're already saying that at STP, our hydrogen atom has to travel 8,370 times its own diameter before you get to the next collision. And I'll also just put in that the typical spacing between atoms is 3.3 nanometers. So that's still, about 250, more than that even, times the distance between actual adjacent atoms. So the atoms are quite small compared to their spacing, means that you travel a substantial distance and you move past a lot of nearby atoms before you finally collide with one. So we can look at this and say, yeah, our hydrogen gas at STP is ideal enough. And of course, all this depends on just how fussy you need to be, but for most applications, that's doing pretty good. All right, so now the next short topic I want to turn to is RMS speed. Oops. And this is a thing that's created to give us a typical value that we can use to describe the motion of typical value we can use to say how fast a typical atom is going. So let's just start with this thought experiment. Think of the atoms of gas in the room you're in right now. What is their average velocity? Pause and get back with me on that. All right. So this is one of those that you're not going to like, but the average velocity is 0. And that's because there's a heck of a lot of molecules in the room. I mean, I'm sure your room is much bigger than 22.4 liters. But even if we just use that, we're talking about on the order of 10 to the 24th molecules in your room. So half of them are going right, half of them are going left, half are going up, half are going down, half are going in, half are going out. Well, the right and the left will have plus and minus signs. So for everything that has a rightward component of, say, 2 meters per second, something has a leftward component of 2 meters per second, and that cancels. And so the average velocity of your gas molecules is pretty much just 0, but that's not a useful number. So what this RMS speed will do is it will give us the average deviation away from 0 in some sense. So we'll be saying that your typical molecule, that although all the molecules will cancel out to give us an average velocity of 0, your typical molecule is this far away from 0. And this comes in from a problem in statistics known as the problem of the drunkard's walk. The idea basically goes like this. The town drunk is getting blitzed as usual, and 2 o'clock comes and they're invited by the person who has basically no neck whatsoever to leave the bar. So they do. And they are so blitzed this time that although they do remember that they live on the same street as the bar, they can't remember whether they live east or west of the bar. So they decide that they'll just leave it to fate. And they pull out a quarter from their pocket and they start flipping the coin. They decide that if they flip the coin heads, they'll go east. If they flip the coin tails, they'll go west. And they'll just let fate guide them. So they flip the coin, let's say, heads, and they walk a block east. Well, because they're so blitzed, the surroundings don't seem familiar at all. They decide to confirm their result with the oracle, and they flip the coin again and say this time it comes up, let's say, tails. So they walk a block west, and they go, oh, wait, this is the bar. I'd better flip that coin again. And the thing is, you can get runs of heads and tails. So although their average position will always be the bar, let's say they flipped heads again and end up a block east. At that point, it's just as likely that they'll walk another block east as they will a block west. So as you increase the number of flips, the total distance that the town drunk can get away from the bar increases. So the average distance so although the average position of the town drunk is the bar, what mathematicians have shown is that the average distance away from the bar that the town drunk goes as the square root of the number of coin flips. And this is sort of characterizing that same idea here. The average velocity is 0, but what the RMS speed will be showing us is how far away from the 0 the average molecule is, how much away from 0 the average molecule is moving at. So let's get into the definition. RMS stands for root mean square. So what this means is you take the square root of the average of the squares of the values. So let's say you have n molecules. The RMS speed, or we often just say velocity, even though that isn't really right, will be the square root of the mean. So to get the average of, we'll say 1 over n times the sum over all of our molecules of the square of the velocity of that particular molecule. So let's say you have let's just say you have 3 molecules, or I'll just expand the series out. So let's say you had 3 molecules. Just you wouldn't use this for 3 molecules. You need a lot more than that, but I don't want to write forever. So if you had 3 molecules, the RMS velocity would look like the square root of 1/3 of the square of the speed of the first one. So that gets rid of all plus and minus signs because we squared it, plus the square of the velocity of the second one, plus the square of the velocity of the third one. So by doing this, we add these up, divide by 3. This gives me the average of the square. And then I take the square root of that. And that gives me the RMS speed. So the advantages of the RMS speed for us are going to be that it's relatively easy to compute. And it'll be easy to plug into kinetic energy expressions since they go as 1/2 mv squared. Because since the RMS speed is the average value of v squared, and for an average kinetic energy, that's exactly what we're looking for, is an average value of v squared. Plugging in the RMS speed for a molecule in the gas is makes this go nicely for us. So there are other speeds, though, that you could say are typical. And so this will get to the third of these, and then we'll see why we just roll with the RMS speed. Because it'll turn out that the other two useful speeds for us turn out to be exact multiples of the RMS speed, which is the easiest one to calculate. So to that end, we will describe the Maxwell-Boltzmann distribution. So the way that you would go about measuring the speed of molecules in a gas, here's an experiment you can do that does this. So let's say you have yourself a small little oven, like so, with a little tiny hole. And we make sure that there's gas in this oven, but with this tiny hole, molecules aren't exactly flying out in a hurry, but they do fly out. Okay, you stick the whole thing into a vacuum chamber so that the molecules that fly out are the only ones we're looking at. So then what you can do is you can measure the average speed of the gas. The trick is as these come out, one classic experiment to do this has what's called a chopper wheel. That looks something like this, and then we'll have another one like so. So what these are wheels, these are discs that have slits cut out of them. And the idea will be that we'll have the pair of slits churning at some known angular velocity omega that we can control. So then only gas molecules of a certain speed that make it through the first one, most of them will wind up just bashing against the plate on the second one because it won't have rotated around in time for the slit to come back through. But occasionally one of them will be going at just the right speed so that in one period it'll cover this distance L in one rotation period. That one will be free to go through and hit our detector. And so then you can go ahead and count how many are going at the perfect speed that will go through that toothed wheel setup. Then you go ahead and you change the rotation rate of that toothed wheel. So now you're picking for a different speed. So this whole contraption winds up getting called a velocity selector for that reason. So that's only letting gas molecules of a certain speed through. And even among that, only ones that were lucky enough to have passed through the first slit in the first place. Anyway, with all of that, what you can eventually do is you can make a plot of the percentage of molecules that strike your detector as a function of speed, and this is usually done as some sort of a histogram. And so you'll have something that maybe looks like, oops, something like that maybe, I don't know. Now, these experiments have been done very carefully, and eventually some workers fit an empirical model to it, which Maxwell and Boltzmann eventually were able to derive. Now, the derivation is way beyond the scope of what we're doing here. But the distribution winds up looking like a bell curve, except it's got this big long tail at the end. I'll go ahead and write the function just for the giggles of it. Now I'll explain what f of v is in a moment here. So this is 4 pi m over 2 pi Boltzmann's constant times the temperature, 3/2 v squared e to the minus mv squared over 2 kt. Yeah, that's a mouthful. Now how do I interpret this? So the way you interpret this is, say you're interested in what percentage of molecules are going at a particular speed. Well, if you say it's at a particular exact speed, the percentage will be 0, because this will be a width of no measure. So what you do is you think about a small interval dv, and then this area under the curve here is f of v times dv, because if we make this small enough, this just turns into a rectangle. And this will be the fraction of molecules with speeds in the range of v minus dv over 2 to v plus dv over 2. Now, real world, you can't measure out to differential regions. So what you can then do is say, oh, the percent, we can then say that the fraction between v and v plus delta v, that'll be equal to the integral dv of this f of v, the Maxwell-Boltzmann distribution, evaluated from v to v plus delta v. So integrate this function over the range of speeds that your instrument is sensitive to. So say, your experimental uncertainty will allow you to bin speeds between 300 and 310 meters per second. You put 300 down here, 310 up here, integrate this, and what will pop out is the percentage of molecules that go between those two speeds. So with that thought, you can find average values of things by integrating that along with this function. So for instance, if I just wanted the average speed, what I would do is integrate over all possible speeds, so 0 to infinity, my fraction times v. So what this is a weighted average. If we think of this as a bunch of sums, what we're doing is saying, like, I'll take the percentage that were from 300 to 310 meters per second and multiply that by 305 or whatever. And of course, when you take that down to differential size, you don't have to get strung out about taking the averages anymore. But then you take the percentage between 310 and 320, multiply that by 315, etc. And when you add all that up, what you'll get is the average speed. You're taking the percentage of molecules at any particular speed, timesing it by that speed, and adding all of those little products together. This gives you the average value. So that's the average speed. Now, I'm just going to say evaluating that particular integral is a royal pain in the butt. But it's totally doable, and so I'll just go ahead and quote the result. It turns out to be square root of 8 kT over pi m, where m is the mass of the molecule. Similarly, we can compute what the RMS speed is. That would be the square root of the average value of v squared. And again, I'm just going to quote the result. It's 3 kT over m, take the square root. And you evaluate these just by looking them up in integral tables. The integral is pretty complicated. So then finally, there is one other speed that kind of makes some sense. And that's this one right here, what we'll call v most probable. So this is the most likely speed you are to be going. To get v most probable, what you do is you go ahead and differentiate our fraction with respect to v and set that equal to 0 and solve. When you do, you get that the most probable speed is the square root of 2 kT over m. Well, you'll notice that all of these have a square root, a k, a t, and an m. And so if we go ahead and hash it all out, just compare all the numbers, what you get is that v most probable is equal to 0.82 vrms. And the average speed is 0.92 vrms. So we'll go ahead and put those in here. So the average speed, sits about here. And the RMS speed sits about there. Now, like I said, it'll be easiest for us to compute VRMS, but occasionally, not in this treatment, but in later courses or other courses, if you need the average or the most probable speed, you can just take the RMS and times it by 0.92 or 0.82. So as long as we know how to calculate RMS speeds, if we need to know the other two, we're good to go. And these are the only other two definitions that make any sense. The average value of the speed or the most probable value of the speed. Well, like I said, we'll be interested in RMS because for energy reasons, what we'll be concerned about is the average value of V squared. All right, that was pretty technical stuff. The payoff will come in the next video when we finally link together Newton's second law and the ideal gas law. So we'll see you in the next video.